Hey everybody, so we are going to finish up our unit on gene expression, and this isn't the most fun topic, but we do need to talk about the link between gene expression and cancer. So cancer, we talked about before, is a loss of genetic control of cell division, and so you have this balance between growth stimulating pathways or accelerators and growth inhibiting pathways or brakes. Now when that balance is shifted, and either cells spend too much time like hitting the accelerator or can't hit the brakes, then you're going to have a problem, and that usually involves a cell growing and dividing too quickly, or cells that won't apoptose or respond to signals for cell suicide, and that's when we see cancer develop. We're going to talk about two different types of genes. The first are proto-oncogenes, and these are normal genes for cell growth and cell division factors. However, genetic changes such as mutations can change these genes into oncogenes, and they are then cancer genes. There's a few ways that this can happen, and so what you're looking at here is the original proto-oncogene, and with a translocation or a transposition, here you can see that there's a new promoter in front of the proto-oncogene, and so now it is you have normal growth stimulating protein in excess. So this is a protein that the cell needs to stimulate growth. However, now you have too much of it. Here with gene amplification, you can see we now have several copies of this gene, and so again you have that normal growth stimulating protein in excess. Here we are looking at what happens with point mutations, and so this is a point mutation within a control element, so something that controls how often this gene is transcribed, and so again it is showing you this normal protein in excess, and here you have a point mutation that is taking place within the actual gene, and it's showing you that it could be either hyperactive or degradation resistant, meaning that that protein won't break down when it's supposed to. So any of these changes can turn proto-oncogenes into oncogenes, because you are going to end up getting that growth stimulating protein in excess, or it's going to be hyperactive, or it's not going to break down when it should. Next we have tumor suppressor genes, and so these are genes that are meant to inhibit cell division. And we have several examples of different types of cancers that have issues with their tumor suppressor genes. So you have RAS, which is a G protein, and when this G protein is mutated, it causes an increase in cell division by overstimulating protein kinases. There are several different mutations that are known to do this to the G protein. Now, in a normal system, the growth factor is going to come in, it's going to be received by the cell. So here you have a protein kinases. They are going to activate a G protein. This is the RAS G protein. That's going to trigger a phosphorylation cascade. It's going to send a signal into the nucleus. So here you have your transcription factor. You are going to transcribe a section of DNA that codes for a gene. Then in the cytoplasm, you will make the protein that stimulates the cell cycle. That's the normal system. However, when this RASG protein is mutated, now you have a hyperactive version of this, and it doesn't require the growth factors to be received by the cells. When this is hyperactive, it's going to keep this system going on its own. So you're going to be continually making this protein that stimulates the cell cycle even when you're not supposed to be. So some cancer examples, P53 is involved with several DNA repair genes and checking genes, and this gene can become damaged. So one example is with cigarette smoke, and when that happens, it can't inhibit cell division. It also cannot cause damaged cells to apoptose at that time. So those damaged cells that should commit cell suicide are not going to, because of that damage. All right, so again, here we have UV light coming in. We can see that we now have damage to the DNA. This is going to trigger protein kinases, which are then in turn going to trigger an active form of P53. This P53 would cause a gene in DNA to get transcribed, and this gene inhibits the cell cycle. So it would essentially turn the cell off in terms of dividing, because the DNA is damaged. You don't want a cell with damaged DNA to be dividing and produce daughter cells with errors in its DNA. That's how the system should work. Again, however, when you have a mutation, in this P53, it can't activate the transcript, and so you're not going to get the proteins that stop or slow down cell division. So this cell that has damaged DNA, it's going to keep growing and dividing and producing daughter cells that have issues with their DNA then as well. So carcinogens are agents that are known to cause cancer. We've talked about some of these in different examples in the class. So when we talked about Rosalind Franklin and how she developed cancer, it was due to her exposure to radiation. But carcinogens usually work by altering DNA or interfering with the control or repair mechanisms. We talked about that because we want to look at what's called the multi-step hypothesis. And this hypothesis says that cancer is the result of several control mechanisms breaking down, usually, all right? And so exposure to carcinogens over a period of time can cause different mutations that will result in several of these mechanisms breaking down. So again, we talked about Rosalind Franklin being exposed to lots of radiation through her work. And that was over a period of years where she was exposed on almost a daily basis. And then she developed cancer very young. So that doesn't happen overnight. So it usually takes several different mutations before cancer starts. Here you have colorectal cancer, and so it's just showing you that you have several steps. So here's the normal colon with epithelial cells. You lose a tumor suppressor gene, APC. You end up with a small benign growth or a polyp. Steps 2 and 3, then you have the activation of the RAS oncogene. You have the loss of the tumor suppressor gene DCC. So now this is a much larger benign growth. Then with the loss of the tumor suppressor gene P53 and any additional mutations, you now have a large malignant tumor. And so this took a while to develop. You had to have several things go wrong in order for that cancer to develop. Something to really keep in mind, though, is that severe damage to a chromosome that causes it to shatter or to have severe errors very quickly could lead to immediate cancer, because you're going to end up having lots of errors all at once. So severe damage to a chromosome could cause cancer to happen a lot faster. And it doesn't always take a long time and multiple steps. Just generally, it takes a while and multiple steps. So can cancer be inherited? Cancer is caused by genetic changes, but it is not actually inherited. However, oncogenes can be inherited. So this multi-step model suggests that this puts a person closer to developing cancer, but it is not a 100% indicator that they will develop cancer. So one example is the BRCA1 gene. This is a tumor suppressor gene that is linked with breast cancer. If you have a normal version of the BRCA1 gene, your risk for developing breast cancer is about 2%. However, if you end up inheriting an abnormal BRCA1 gene from a parent, that you then have a 60% risk of at some point in time developing breast cancer. So it does tend to run in families, but it is not a guarantee that breast cancer will develop. So some people have been known, I know I'm covering part of the text there, but some people will have breasts removed just to avoid the cancer risk. So you can have a double mastectomy, remove both breasts if you know that that abnormal BRCA1 gene runs in your family, because you are at a much higher risk for breast cancer at that point. All right, so things that you should know for this unit. You need to know the operons. So you need to be able to talk about the lac and trip or inducible and repressible operons. You need to be able to discuss several different mechanisms for gene expression, especially with eukaryotes. So we had a lot more examples for eukaryotic gene expression. So be familiar with those, make sure you can talk about them, and also understand the multi-step hypothesis. So your lecture question for today is, if a friend told you that they knew they were going to get cancer because a grandparent, for example, had cancer, and they say it's genetic, I know I'm going to have it because my grandma had cancer, how could you explain to them what their actual risk would be for developing cancer? So I want you guys to take a minute, think about that question, and then please send me an answer via the class website. Thanks, guys.